Thank you, Professor Liu, and I appreciate the invitation to speak about some of the research we've been doing over the past few years here at Illinois in cooperation with the University of Michigan Center. And it's great to interact and hear about all the great developments that are going on both with the vehicle, transportation in general, and how possibly my background in research can fit into this and complement all the other research. So really today's talk is really about how the roadway can be most used to help with autonomous vehicle navigation, maneuvering, guiding. I'm going to stick to the lateral positioning, a small part, which is an important part, and offer some ideas. I'll show you some of our early ideas that we worked on. We continue to work on these ideas to make them better, more robust, more reliable, and more efficient. Really the message today isn't that whatever I'm going to present is replacing what autonomous vehicles can do right now with their own computer vision and algorithms, but to just complement it so that the reliability of vehicles traveling can increase further. And there's confidence with agencies, confidence with drivers or people in the vehicles that they're really going to be more safe than they currently are with human drivers. So that's kind of the objective. And I started thinking about this doing my research in concrete materials and pavements, and then later teaching geometric design classes, is how this is an exciting technology, a really revolutionary technology of how we move, and how does the road fit in all this? How do the roadway materials fit in all this? Is kind of on my mind for a while, and we actually started asking students in the geometric design class about 5 years ago, how would we design the road differently? About the same time we were thinking, well, how could we use the road materials as a way to give feedback to the car, essentially? And that's kind of where these ideas came out of. And I'd like to acknowledge the Center for the financial support, as well as Sachindra Dahal, who's my the co-researcher here. He's a PhD student in our department, and he's has a great background in his like and desires in sensing, as well as he's a civil engineer and he worked in materials, so he's got the right skills to kind of help on this project and move the developments forward. So really it's been an exciting time learning about autonomous vehicles, what they can do, how they really increase safety and mobility, as well as reduce a lot of the things that the traveling public doesn't like, including excessive fuel consumption. So that's really on the, there's so many positive sides as you talk to the general public, as even I do, and students, about just safety. That's super important that autonomous vehicles can bring to bear. But one thing that strikes me is that the number of centerline miles of roadway in the U.S. is around 4.2 million centerline roads, and we know a lot of the vehicles stay in the lanes, maneuver and guide based on lane markings and being able to keep safely within a lane. And yet we see over 70% of our roadways are local roads and streets that likely have limited lane markings on them. And so it becomes a real challenge to only rely on lane markings as the primary way of keeping the lane. Of course, it's an essential part for a lot of our high speed, high vehicle mile traveled functional classes, and they have generally very well marked lanes and good signage. But as we move down the functional classes that I list here, obviously the reliability and having uniformity kind of goes down. And so if we want to provide the public assurances, I think the idea here is kind of complementing in a cost-effective way, a way of knowing where vehicles are such that you can still drive the vehicles if you had some confusion in the computer vision or adverse weather conditions. So as everybody on the call generally knows, we have the automated vehicle part and we also have the connected part. And I think there's a lot of talk on the connected part, connected to V2V or vehicle to infrastructure. And really what the talk is today about is having the vehicle, the automated vehicle, talk or passively sense the roadway in order to figure out where its lateral position is in a way that's relatively simple. I mean, it won't be zero cost, but it's not as, it can't be super complicated and it can't be super expensive. So we know all these sensors on the vehicles really play a great role in a lot of the things that everyone knows is super important about keeping people around the vehicle safe, as well as the people inside the vehicle, and being able to avoid obstructions and also be able to just navigate where you're going, including all types of sensors, from radar down to ultrasonic sensors that work pretty closely when obstacles are nearby. And that information is also very important as we try to plan the vehicle movements, whether that's at high speeds or low speeds. And it obviously is used to execute commands of the vehicle. So that's all pretty well known and not really my field. But as we think about now just staying in the lane, and we'll focus on that part because this is the part the research is focusing on, is generally, obviously, you can, GPS allows for very good navigation, but the camera really keeps you in that 12-foot lane generally, and avoids going off into the shoulder or into the other lane. And so really it does a really good job. And the question is, can we rely on that enough in all functional classes to be safe and not have any problems? And of course, the question rises about what happens if the lane markings aren't there. Can it do a very good job? And in some cases it can if there's enough contrast. But on the flip side, if we have adverse weather conditions, which I'll show here in the next slide, so we do have lane marking issues. Sometimes they don't exist. As well as rain, snow, fog, ice. All these obviously kind of cover up the lane markings and can confuse where vehicles are, as well as they can have adverse effects on the navigation system. So there are issues, and what percentage of the time it'll occur really depends on the season and the location in the country. But we know, if we live in the U.S., that there's a significant number of states that don't have clear skies and very little rain or snow most of the year. So it is a real challenge in Michigan and Illinois, the Midwest for that matter, that we will have challenges with a camera being our primary vision to make decisions, especially when it's hard enough for humans to drive on ice and snow-covered roads. How are autonomous vehicles going to do that, especially on local roads and streets where there are even less features that can be picked out? And so this isn't necessarily a new finding that I'm talking about here. People knew about this, people have known about this, and there's been research out there looking at past attempts to basically supplement some of the data that's being gathered with the camera, coming up with 3D maps that can kind of help during inclement weather, whether it's rain or snow, whether it's filtering out information that comes in from let's say a LiDAR when it's raining or snowing. But all of it is time intensive and more it's fairly complex. So it's not preferred, at least at this stage, to go that route. And even embedding sensors in the road seems like a relatively good idea to most people, but it has its own set of what do we put in, how often do we put it in, how long is it going to be there, and then embedded sensors, you obviously would want them not to require maintenance or a power supply, because that becomes really complicated. So that's probably why the dedicated short range communication ideas or cellular 5G networks is makes sense to some degree, that at some point you can have external roadside units that give you information. And so I'll throw that out there, that the potential in the future, especially in urban areas, to navigate, talk to other infrastructure or pedestrians or people, bikes, vehicles, et cetera, is going to be very useful and very helpful in the safe operation in heavily urbanized areas. And so this development will only help, in my opinion, what's going on. But we still have this idea that we still have a lot of non-urban roads or local roads and streets, and even collectors that need to be dealt with, especially in adverse weather conditions. So really, my kind of pitch here is that we really need some sort of passive system, and obviously putting, in my opinion, putting sensors in the road that are active doesn't seem to make sense, and people have looked into that before. And it has to be relatively inexpensive, and the vehicle has to be able to basically reliably detect where it's at in the road, especially if for some reason it begins snowing or icing, or have a fog, and safely stop the vehicle or get it off the road so there's no accident or any other wrong maneuver. And so the question is, ironic, this isn't new. In fact, it was kind of ironic. I did a postdoc at University of California at Berkeley back in the late 90s, and Path Lab, the Path Research Center, was actually right next to the building I was working in paving materials. And I remember seeing all these magnetic markers in the roadway for the Path vehicles back then. And essentially, they put in these permanent magnets into the roadway every so many feet, and then the vehicle could detect these magnetic signatures and be able to basically maneuver in the lane, and at some level know when you hit intersections based on the polarity of the magnet. There was a little other work done at Min Road with magnetic tape that possibly could help with snow plows. I think it's been done in a couple other locations where magnetic tape could help snow plows stay on the road when they couldn't see the edge of the pavement. So yeah, so Min Road had, they actually didn't report this working that great, this magnetic tape, although it seems, looking back at it, that it was working fine. They were just not using it correctly. And likewise, Path, really came up with some good ideas, and they essentially found, though, a lot of these sensors would break, and one of the ways they sensed these sensors was also to take readings of the background noise, and the background noise can vary, and it can kind of shadow, and it can change, and depending on where the vehicle is located, and so you have to know the background magnetic noise as well as the sensor noise. So there was a lot of issues that caused this to seem not to be the right idea at the time, as well as the developments that came later with computer vision. And so really the question now is, looking forward, as maybe the answer is supplementing computer vision with some sort of passive sensor, similarly what Path was thinking about originally. But currently, we really don't communicate. If you think of the lane markings, that they're actually part of the communication with the vehicles in terms of they're finding the edges of the road. So that is a good thing. So definitely the lane markings is essential, and their maintenance is essential in the long term. But the proposal here is to create a signature within the road that hopefully doesn't need to be maintained very often, is easily detected and can be placed in the road such that the vehicle, as a backup system, can kind of know where it is laterally if you have adverse conditions and or you lose some other type of sensing capabilities on the car. So can we change, in the picture on the left, you see a vehicle where maybe you change the properties at the edge of the road so the vehicle can sense, or in the middle of the road. We prefer the one on the right, where your vehicle has some sensors that's detecting passively what's going on with this electromagnetic properties. And the thing with the Path is they were putting in permanent magnets into the road. Here we're talking about possibly using construction materials that are currently used and known about to create electromagnetic signature that the vehicles can detect with relatively inexpensive sensors. And so that's the idea. So imagine you could put in for concrete steel. This is not the only options. I'm just listing a few. Steel fibers or steel slag aggregates. Both of these can be have electromagnetic properties, conductive properties, and they can be constructed in new roads, or they can be retrofitted in the past. And they don't require any power. And generally, once they're there for a relatively long period of time and don't need any maintenance, unlike pavement markings, which need to be maintained pretty frequently. So we're really trying to establish here weather independent kind of maneuvering in the lane. So here's a schematic of what I'm really talking about. And this is similar to what PATH was doing, except now we're talking about a continuous material placement in, let's say, the center of a lane. This is a 12-foot lane width. If you put in some kind of higher conductivity material, let's say steel fibers, and you can detect that, you can detect a higher conductivity material versus the remaining part of the road is relatively low conductivity. Asphalt or concrete is relatively low conductivity. You can then pick up where the vehicle is relative to the center line of the road and be able to at least react to its movements if it's moving outside of the normal lane wandering of a car. And so one method that many of you may have heard of and may know pretty well is been around for a very long time, is essentially eddy current. And essentially you have a coil that under a change in magnetic field induces an eddy current in a conductive material below that that doesn't have to be in contact. So if you think about your basic metal detectors on the beach or anywhere in the grass, you essentially have a coil and you're trying to detect some sort of buried metal in the material. And this could be in the road. So you could use different types of metals, but the key there is you have to have the right balance in how you're building your coil, how close it is to the surface, how much current you're putting in there, as well as what the conductive metal is, as well as its kind of geometry. So those factors playing into the role of this successful. So the idea that I'm presenting today is this is one idea to think about as that shows the potential of a lateral positioning of using eddy current within materials that you could place that are known. So most of the materials I'm talking about are known in the construction of pavements that can be retrofitted or placed. And just as I was saying, that if we had an eddy current sensor that was placed on the vehicle, we know that the magnetic field it creates is a function of its current. How many wires are in this loop? This blue loop here is the kind of the eddy coil, or the coil that's passing the current. And the target material is our road, where we have a little slice of the road. Essentially, we don't need the whole road to actually be of the target material. And the radius of the coil makes a difference, and the height above the coil, the Z distance here, makes a difference. So we can't put it 2 feet above the road, and obviously we can't put it 1 inch above the road for other reasons. So this requires some balance. And this just gives an example of the circuit we have that operates at 200 hertz. And essentially this coil, you see, we're moving the concrete that has steel fibers on the right towards the coil. That's not exactly, it's just showing here that this device, when it turns blue, means the coil is kind of close to it at this point. So this gives you an idea of how an eddy current system could potentially detect, in this example, steel fiber reinforced concrete that's made in a very small block of material. So this is kind of our setup to kind of prove this concept, and theoretically it should make sense that it works. And this is just kind of demonstrating. We have an aluminum frame here, and imagine this this coil that you see, the circular coil is on your car, on your autonomous vehicle, and the concrete you see below is essentially the pavement you're driving on. And as the vehicle tracks laterally, it'll pick up this this thin notch in the middle here, which is made of a conductive material. It's just steel fibers in this case. And one can imagine ice or snow or water or debris on the road that may even be covering this conductive material. So we need to make sure we test that to make sure that we can still pick up a signal even with adverse weather material on the roadway. So this gives a schematic of what you were just seeing. The key here is we want to do this is very non-evasively. We don't want to have to tear up the whole roadway for whatever technique we're going to use. This technique is based on eddy current. There's a couple other ideas we have as well, but you want to be able to minimize the impact on the roadway because that'll be highly costly and highly costly to maintain. So for example, we made 3x3 prisms, which is on the right here. So this is of that material like steel fiber reinforced concrete. We had a slab that we could just put in different size prisms and then detect it. So ideally the smaller the prism, the better, because we use less materials. We don't have to remove very much of the existing roadway, but we like the idea of it being continuous. And from our initial testing, we saw that we could scan anywhere between 5 and 7 inches above of the surface and pick up a relatively good signal. Obviously, if you change the setup of the coil or the current, you can change the height that you can detect from, but this is what we currently used in this particular study. The other factor here is how much steel fibers. So not only the geometry of the conductive material, but how much volume of conductive material. You'd like to minimize the amount of conductive material because that's costly, but you need to have a minimum amount such that you can detect it as well. So the other thing that we wanted to address was this whole topic was really about adverse weather conditions. So what if we had water or ice on the surface of that slab covering that conductive material? Would that affect the signal at all? Because we want to be sure that this is robust under any weather conditions. So we placed ice and water over that conductive material that was in there for different notch thicknesses. We actually even put recently some sand on the surface as well. And so this gives you some idea of what we're doing. So we're scanning the surface, and that green area that you see there is essentially that small 1x1, 2x2, or 3x3 inch notch. And we do some transverse scans of that material. And so if we do a transverse scan, you get a plot of distance, so going from one side of the slab to the other side laterally. And when the coil gets over that conductive steel fiber reinforced concrete, you can see the signal is at its maximum. And note, this is for 3 different steel fiber amounts, okay? So the first amount is, the highest amount there is 1%, which is pretty high. We normally wouldn't build concrete roads out of 1% steel fibers. 0.5% is the lowest target here, but still detectable. And 0.5% would be something that you could see on roadways, on overlays with steel fibers, or even industrial floors. So that's very doable. 1% is a little more difficult, but doable. And you can see that no matter what signal, what fiber volume fraction for this prism size, we can detect it. So that's encouraging. The other thing would be if we change the coil height, and theoretically it should change, and that's really what happens on the experiment. So if we go from a 5-inch, which is the solid line, down to 7-inch or up to 7-inch height of the coil, obviously the signal's attenuated, but still detectable, even, and this is with 1% steel fibers. If we use smaller notches, which would be ideal, the smallest notch here is 1.5 inches, slightly different than our 1 inch. But if you go to 2.5 inch notches or 3.5 inch notches for eddy current, you can see the signal strength is really high. So there's some, I think the point here isn't that there's a solution that I've presented, but you can balance the eddy current sensor with what you're going to put in the roadway to detect the right level of accuracy of the signal, so you know where you are laterally within the roadway. And just so we verify that water or ice. It can detect when those are placed over the roadway. So even a 2-inch deep water placed over the road here with a 3-inch prism, 1% steel fibers, still has a signal. It's attenuated from no water, obviously, but it's still detectable. Its dielectric is quite high. Ice, on the other hand, has very low dielectric, so actually it has almost no attenuation of the signal. It doesn't have any attenuation really of the signal. It's fairly close to air, ice is, in terms of its dielectric. So we see a very good signal even with ice. So your computer vision may not work with ice, but dielectrics or any conductive material, assuming it has a minimum amount of conductivity, would be detected with the eddy current. And this figure here is really just a summary of what I just plotted. And it's going to show you basically that the most sensitive parameters here aren't necessarily the adverse weather conditions. So whether we have ice or water doesn't drop the signal attenuation. So high here means that there's a potential for high signal attenuation. So less fibers or higher coil heights or higher depths of water would attenuate the signal. And you can see here the most sensitive factors are factors that the engineer can design, whether it's how much of the cross section of the road has to have some conductive material, or how high the sensor is above the roadway, as well as how much fiber, steel fiber, or other, let's say steel slag aggregate would be another type of material that's a byproduct material from steel manufacturing. They create slag aggregate that has some iron in it that can be detected potentially with eddy current. So these are really makes it nice that this electromagnetic material actually can help us with detecting our lateral position. Now, there are some trade-offs with eddy current, and I'm sure when the Q&A session comes up, maybe some of you will figure out that there's some limitations with eddy current. Obviously, if we want to detect deeper from the vehicle, we need to have a larger coil or more winds, and of course, some of the vehicle parts may be conductive, so that's going to raise some other problems. But also the conductivity of the material matters, as well as the geometry of the material. So steel fibers work nicely because they're relatively long, and so they produce nice eddy currents that can be picked up by the sensor. If you tried a different, the same material that was, in microparticles, micron-sized particles, it wouldn't really work that well. It doesn't create eddy currents that allow the electrons to flow. So basically, I hope this kind of, the eddy current shows to the audience here that lateral positioning, by changing some of the construction material properties and then having the vehicle sense that as a complementary system to the current autonomous vehicle sensor suite is kind of attractive, especially if you don't have confidence in your lane markings or your edges, or the fact that the adverse weather conditions are going to make AV driving a little bit more less reliable. So one last note here as we discuss, how this would look in the field if we placed this material, a conductive or electromagnetic material. We tried this recently just as a proof of concept of putting a material in the electromagnetic material in the middle, and just showing that the vehicle path could be detected with electromagnetic material, given you drive a short distance. This is just a cart that we'll be showing, but it gives you an idea that the computer vision, the optical approach with a camera and lane detection kind of breaks down at times, and you need to have another backup system. So this figure on the left here is really kind of showing location, what a algorithm would do to find edges, and it gets confused at times because we do have an electromagnetic tape in the middle there. But on the right here, we have we kind of detect that EM tape and I'll run it again just so people can see it. So this would be no lane detection, and this is the algorithm to try to find the edges. So the vehicle would be kind of confused where the middle of the lane was. Whereas on the right here at the top, you see the little indicator showing where the vehicle is as it moves in a meandering path along the way. So I've only shown this, in this particular case, I've only shown the meandering path. So this system, when you can't detect accurately with the computer vision camera, you can easily pick up with some electromagnetic material that's placed in the lane. So hopefully what I've shown today at least gives some hope or different thinking of how the roadway outside of the lane markings can be used. And there's still a challenge here that although I would argue that we can use the roadway as a passive sensors, we can strategically place some electromagnetic material longitudinally down the roadway. And it can serve as a complementary system for lateral positioning and maneuvering when you do have adverse conditions or when your other sensors may not be functioning correctly. You still have a lot of lane miles of road to deal with. And so there's no getting around that. But I do think that the maintenance side, if you think about maintaining lane markings on all classes of roads, all functional classes. So if I'm going from my house to Chicago, how many local roads I would take to get there. Obviously, the principal arterial, the interstate, would be the easiest because usually the lane markings are maintained pretty high, but the local roads and streets aren't. And so the idea that we could create these types of passive sensors in the local roads too is somewhat attractive in that they wouldn't have to be maintained as readily as lane markings do. So my pitch is really modifying the road here strategically and gives us enough time to maybe create these network of sensors that are on roadside units that will take years to put in place by really using construction materials to create kind of a passive sensors to help us with the vehicles. So I'm kind of excited that maybe this has a piece of the puzzle to seeing more readily adoption of autonomous vehicles, at least for certain networks of roadways, relatively soon versus waiting till we have everything in place in all functional classes. And I think I got done a little earlier than I expected, but that's all I have. I'd like to again thank Sachendra Dahal, the PhD student who's put together a lot of these slides and videos. And we've left some, I'll be able to give the presentation to the center and they can give the slides out to whoever like them with some of the references that are in there from previous studies. So thank you, and I'll be happy to answer questions as they come.
Thank you very much, Jeff. I see two questions from the Q&A, and I'm going to read it to you. Are you interested? The first one, are you interested in on-road pilot as a next step? Have OEM being engaged? So I think it's a very good question for you.
Yeah, I would say we've taken what I've shown in the eddy current example and taken it much further. And I didn't present our latest setup that I think is even less evasive than the ideas I've shown with steel fibers. And I would say we're pretty close to what the questions were asking. We've done some work with a new sensor and materials that we believe, yeah, are pretty close to being, I would say, piloted on, not on a real road, but definitely on a test track of some sort would be nice. And that's part of Sachendra's PhD, is to put that down and see how it could work together with an autonomous vehicle.
I think for your contact information, I think it should be easy to find Professor Roesler's contact information. Just get you engaged in terms of any of the pilot test. There's another question on, did you do experiment with reinforced concrete too?
Oh, that's a great question, because yeah, if I mean, that's kind of where eddy currents break down. Whoever asked that question knew that it would be problematic with a lot of reinforcement, because they would generate eddy currents and very, they would obviously cause a major problem. So that's the main limitation. And now, not most roads aren't continuously reinforced, which would be the main hurdle. But you do have bridges, you do have joints with steel in them periodically. So it's not a trivial matter, and that's probably where I think long-term eddy current, that's kind of where we left eddy current, even though it shows the concept. It probably has a lot of other things to overcome to make it work, and so we thought about another approach that's similar but doesn't use eddy current.
Okay. And by the way, and I think Professor Roesler has already put his email on the chat, so you should be able to find it there, his contact information. There's a question on how do you foresee that the path to implementation playing out, for example, federal regulations, state level regulations, and private enterprise, etc.
Yeah, I've thought a little bit of that. I think, I'll give my opinion. I think state agencies, take a long time to implement for good reasons. I mean, they're responsible for the traveling public. So yeah, there may be pieces on the federal level, but one thing I do like about the system this system is, it's something the state agencies already know how to do. They already know about construction materials, they know about maintenance, they know about the materials we're actually talking about, and they just complement the vehicle. And I think really the piece that I don't know, and this would be with the vehicle sides, is really the reliability in adverse conditions, and whether the claims that I'm saying and with the claims of the autonomous vehicle manufacturers, if you fuse those together, will that be the confidence that's needed to set up a network? That's how I see this rolling out, is a network of autonomous vehicles, roadway that you can designate like an interstate. So from Chicago to Champaign or Chicago to Ann Arbor, there would be a roadway you could take with your autonomous vehicle where it could not have a driver. I mean, I think it has to roll out like that, where you can do the roadway upgrades that are needed, both in the lane marking side as well as these passive sensing ideas, and then the road kind of be designated as an AV road. That to me seems to make sense, and agencies can get on board and get more confidence that they're working as they move down to lower and lower volume roads, which have more and more uncertainty in terms of how you're going to both pay for it and implement it. But most of the vehicle miles traveled are obviously on your arterials, so doing the implementation on the arterials shouldn't be as hard, and it's not as many miles of roadway, so you should be able to have a high impact pretty quickly.
And I see another actually related question. What about the maintenance issue? Road work, degradation, etc., may adversely affect the sensor.
Yeah, that's a good question, and there's another question on freeze thaw to the same question. I mean, right now I'm showing concrete, but we could talk about asphalt too. As long as you have something conductive or electromagnetic in asphalt, you can do the same thing. And what I think is an argument for this idea is that whether you're using concrete or asphalt, we're pretty, the general public would say the roads are not in great condition all the time, but generally we're pretty good at predicting the maintenance cycle on roadways. So I'd say those are going to be much longer maintenance cycles than putting lane markings or anything else on the roadway. So my confidence level that we could, for instance, for concrete roads, we could give almost low maintenance for first 15 or 20 years for something like this. And that's huge when you think about what's going to change in the next 15 or 20 years. So I don't see for instance, steel fiber reinforced concrete, if that was a solution, which I don't think it is, but let's say it was, I'm very confident that that would last 20 years with limited maintenance. Are there roads that fail before 20 years? Yeah, but I'm talking about the majority of the roads pretty much stay together for 20 years. On the concrete side. On the asphalt side, you could make a similar claim with a similar number of years. That's pretty extensive and much greater than anything with lane markings or any other signage on the side of the road for that matter.
So how about the freeze-thaw cycle? Does that really gonna deteriorate the material?
Well, I mean, freeze-thaw does deteriorate concrete. It has less of almost no effect on asphalt, except for some cracking. Yes, freeze-thaw does have an impact on concrete, but it won't have any more impact than it currently does on our roads. So the design life of all major pavements are at least 20 years, and the service life, if we're talking service life on principal arterials, they're probably 40 years currently. So imagine if we put something down, I mean, we can expect at least 20 years to be there easily. And that, I think that window is huge when you think about deploying autonomous vehicles and having a kind of complementary system to some of the challenges right now.
Yeah, yeah. So
I don't see it as an issue. Yeah. I don't really see it as an issue.
Since there's no question from the audience, I actually have a couple of questions. I find that your presentation is very, very interesting to me. One of the things I feel is that in traffic flow, in traffic performance, studies, we use loop detectors, and so that this is actually a reverse of the loop.
That's right.
Backwards. You put exactly. You put the loop in the vehicle. You put the metals on the road. So it's exactly the inverse of that. It's outstanding. Brilliant idea, I think. It's very interesting to me. One of the things you mentioned that you will create signatures, right? So the inductance signatures out of it. And are you using the signatures to identify the position of the vehicles? Is that what you do? If you do, then do you need to map out these roadways first? Is that right?
No, you don't have to. I mean, whether it was with eddy current or, I mean, imagine if you had I'm not an electrical engineer, but you can imagine 3 or 4 of these sensors on your front bumper, or a different type of sensor that maybe detects magnetic material, for instance. And you're basically, as the car moves, you're detecting which sensor on your bumper essentially is in the middle of the road, essentially. And so there is no background I should say, with eddy current, you probably would have to drive the road, because if you had continuously reinforced concrete, it would create a major problem because the steel the steel below could potentially become a problem. But like in the PATH program, they were using magnetic sensors, and anything with that's ferromagnetic in the road is going to really disrupt the signature.
Yeah, what I was thinking is that I think you mentioned lateral positions. Yes, I think lateral position you should be able to figure out in terms of the center line. But I was thinking
longitudinal.
Yeah, I was thinking of longitudinal, and then really the signature coming out of this. Each prism you put it over there, it might be different, and then you actually can generate a signature that you can identify longitudinal locations.
Yeah, I think that's very possible, and it's the easy analogy is what was done at Minroad, where they actually took the magnetic tape and they changed the dipole moment, periodically from positive to negative down the tape. So you can create signatures with, for instance, magnetic materials that go longitudinally. So it tells information like a code.
Exactly.
With the material. So, I mean, it's easy to do with permanent magnets because, they can be magnetized to be a certain direction, and tapes can do that. I still think you could do it with natural materials. It may be a little bit more creative how you do it, but I think it's possible.
And how many of the coil you want to put it in the vehicle in terms of 1 or 2 or 3, and how big is that?
Well, yeah, I mean, my opinion at this stage, because a lot of this work was done in the last year, is that there's probably better ways to do it than using eddy current. So I'm not pursuing eddy current, even though I showed all this. I think it can work, but it would take a lot more work to implement it than, let's say, another type of non-contact sensing. But I still think you need to have multiple. So let's assume eddy current works because we're using another sensor now. But you still need multiple sensors on the front of the car to, and we haven't optimized that. We're currently have a system, and I think there's 10, but I don't think you need 10, but we're using 10 on a bumper.
Yeah, how big is that, each of these?
Well, the sensors we're currently using are fairly small, the size of like a USB drive. Eddy, yeah, if we had 10-inch eddy current coils or 12-inch, you couldn't get that many on the front of your car. And frankly, yeah, I mean, you think about all the metal in your car, it wouldn't work.
Right. Okay. And I see there's a question coming from the audience. What about the interference with sensors in the adjacent vehicles?
Yeah, I mean, I don't think, I mean, eddy current's pretty, if you design the coil to really look at a certain area. So if you're outside that area, it's like you don't exist. So I don't think your adjacent vehicle wouldn't necessarily be a problem with eddy current or our current sensor. It would be really stuff that's in the roadway that's going to be more of the problem, or in the current vehicle that you're driving. That would be, you'd have to worry about shielding of the current vehicle versus other vehicles, unless I'm missing something about how other vehicles can distract the sensor. I mean, I don't think there's any reason why it should.
Okay. I don't see any other questions, and I think I want to thank you very much for your presentation. I feel it's a very interesting presentation, and in general, I think how infrastructure going to adapt and help deployment for autonomous vehicle is a great research question, and I think also I do think the solution you propose has a lot of potential to be implemented in the real world.